we're going to introduce the idea of planes, that's a flat two-dimensional surface within a three-dimensional space, by trying to write the three different types of equations you can use to describe a plane. So the first thing you need to sort of understand about planes in three dimensions, this screen in front of me is a two-dimensional plane, right? It's flat. You can go this way or you can go this way. But it exists in a three-dimensional universe, right? I can move my finger away from the plane and towards the plane without having to travel within it. And that's a new feature of three-dimensional geometry. When you were doing the x and y axis, the Cartesian plane, there's that word again, Cartesian plane. Because you only had x and y coordinates available to you, you couldn't leave the sheet, right? You were stuck on the piece of paper with your x and y axis. Now that we're in three space, we're allowed to have a grid, a Cartesian grid, that's off and tipped and runs wherever you like relative to the central origin. So how are we going to write that equation? Well, the simplest one, the vector equation of the plane, is probably the most direct one to understand. So first thing, I'm going to use the tip of my nose as the origin because, as you figured out by now, I am obviously the center of the universe. But if I do that this is the center of the origin, and I'm trying to describe this plastic surface as a plane relative to where my nose is, the first thing I need to do is I need to get from my nose to the plane. So there's some vector from my nose to here. Let's say it's 2 in the x, 3 in the y, negative 5 in the z. And this is from my nose to the board. My nose to this dot. Okay, good. So what I've accomplished then is I have reached the plane from the origin. I'm now there. I landed on my screen. From there, I need to be able to travel in any direction I like along this surface. Now, because it's two-dimensional, I need two vectors in order to do that. You might make the less interesting choice, right? Maybe one goes this way and one goes that way. You could do that. Or you could do them like this. Or you could do them like this. It doesn't really matter. You just need two vectors that lie in this plane, right? These two vectors are parallel to the surface I'm trying to describe. So let's just go with the drawing I have there. So let's suppose this one is traveling from this dot to that dot. We'll call it A. And it's going to have coordinates 1, -2, 5. And this one here, we're going to call B. And they're going to give it coordinates -3, -1, -2. So what I've accomplished then is I've established that every point on this plastic surface can be constructed using this vector from my nose to the dot, gets me to the plane, and then some combination of this and this will let me land at any location I like. For example, let's see, let's try and go like here. Well, how do I get here? Well, it looks to me like if you went from my nose to this place, so if I went, how am I going to write this? From my nose to this place is 2, 3, -5. And then I took a step on A, and then I took another step on A, so that's 2 A's there. And then I took a step backwards on B, that's a -B. Take another one, that's a -B. Take another one. Well, I've landed there. So this, a negative b, a negative b, and a negative b, that's negative 3 b's. So I managed to land at that point, and all I needed was how to get to the plane from the origin, and then I needed to have a set of basis vectors, that's what these two things are called, that allowed me to take steps within the plastic sheet in order to land at the place in question. So if I were to write out what I did here, I did the nose to glass, that's here, and then I added to that 2 steps on 1, negative 2, 5, and then I subtracted 3 steps on negative 3, negative 1, negative 2. So you notice that all 3 of these pieces were needed. I couldn't get to here without the nose to glass vector, because if I hadn't used that one first, starting at the origin, 2a and negative 3b is here, right? And this place out in space. It isn't actually in the plastic plane. So I needed this one to get to the plane. Get to the plane. Once I got there, right, once I made this trip, this vector wasn't enough, right? Adding more and more and more of these would make a line, but that line wouldn't go through this point. It would either go off that way forever or come back this way. And so that's not helpful. I couldn't use just this one. That makes a line this way and that way. It doesn't actually go through my point. But with a combination of them, I can reach any place in this plastic, right? If you start thinking about allowing myself to take half a step of this, or 7/8 of a step of this, or negative 0.0493282645, right? Like any number I like, I can nudge in this direction just a little bit. I can nudge just a little bit to get anywhere on this plastic sheet. So these two things here, those are direction vectors, the same way that we had direction vectors in lines, but in a plane, you need 2. Right? A line is a one-dimensional shape, it needs 1 direction vector. A plane is a 2-dimensional shape, so it needs 2. Just going to label those up there. Direction vectors. That's this and this. All right, now when we wrote the equation of a line, when you wrote the vector equation of a line, I took the starting point, right, get to the line in the first place, and then I added some number of these. I put in an n. And then I added some number of these. And when I did that, it got me any place I wanted on the line. If I put in 2 different parameters with 2 different direction vectors in the starting place, now I can get the vector equation of a plane. So that's this first one, the vector equation of a plane. I'm going to clean up some space here and then maybe do an example of one. So the first equation we've got there is this vector equation, right? And all you need to build a vector equation is a vector that gets you to the plane from the origin. That was this one. And then you need 2 direction vectors that are parallel to the plane. Tack on some parameters there, allowing you to take as many jumps along this as you like and as many jumps along that as you like, and you are finished. There's the vector equation. And when you had the vector equation of a line, you were able to take each variable independently, the x coordinates and then the y coordinates and the z coordinates, and write them out on their own. And that made for you a parametric equation. So I'm going to give you that here. So in this particular example, the x values would be 2 plus 1n minus 3p. The y values would be 3 minus 2n minus 2p minus 1p and the z values would be negative 5 plus 5n minus 2p. So there's two equations for this particular plane that I developed just randomly on the board. The third equation that we're going to have to learn is called the Cartesian equation. Now this one takes a little more work and it's a little more tricky to explain. The idea is that this screen here is composed of an infinite number of vectors that are all parallel to it. They all lie inside of it. And so that's really what a plane is the collection of an infinite number of vectors that are all pointing parallel to one particular surface. And what the Cartesian equation does is it takes that parallel surface and it takes one vector and makes it perpendicular. So this one vector defines this entire plane because everything in this plane must be perpendicular to this vector. That's the idea. It doesn't matter where I put it, and it doesn't matter which direction I head from that vector, I will be traveling perpendicular to this thing. So that's the trick for a Cartesian equation. So in order to get that, I'm going to need a vector that is perpendicular to both this and this. And that's what cross product is for. So I'm just going to do a quick cross of this versus this and see what the vector I get is that's perpendicular to both of those things. So let's go 1, negative 2, 5, negative 3, negative 1, negative 2. Copy the x column. So my x coordinates will be 4 minus negative 5. My y coordinates will be negative 15 minus negative 2. And my z coordinates will be negative 1 minus 6. 4, negative 5 is 9. Negative 5 plus 2 is negative 3. And negative 1 minus 6 is negative 7. All right. So that that vector there, 9, negative 3, negative 7, is allegedly perpendicular to both this and this. And we should check just to make sure I've done it correctly. So 9, negative 3, negative 7, dotted with 1, negative 2, 5. Would be 9 and 1 is 9, 3 and negative 2 is 6, negative 7 times negative 5 is negative 35. So something has gone wrong here. Ah, got it. 15. 5 times negative 3 is negative 15. Negative 15 minus negative 2 would be negative 13 here. How does that change our negative 13 times negative 2 is positive 26. 26 and 9 are 35 minus 35 is 0. I am glad that I checked. So that vector there is perpendicular to 1, negative 2, 5. Let's check the other one. Negative 3, negative 1, negative 2. 9 and negative 3 is negative 27. Negative 13 and negative 1 is 13. Negative 7 and negative 2 is 14, which is 0. So I've got it. So what I've learned then is that if this screen here, this plastic surface, is defined by this vector, 1, negative 2, 5, and negative 3, negative 1, negative 2, then the perpendicular vector, the one I could stick on this plane and define every other vector, is 9, comma, negative 13, comma, negative 7. And we give that a name. It's called the normal vector. Lovely. So now that I have this, the way you set this up is that the coordinates of the normal vector dotted with any other vector in this plane has to be 0. Just lost my markers here. There we go. So if I were to take this normal, 9, comma, negative 13, comma, negative 7, and I were to dot product it with every vector in the plane, I should get 0. So if I do that, I do this little expansion here. So 9 times x would be 9x. Negative 13 times y is negative 13y. Negative 7 times z is negative 7z. And that should equal 0. So by doing this, I have coordinated this plane and this normal line so that any vector that lands in this plane, if I put its coordinates in there, x, y, and z, I better get 0. And if I don't, then that vector is not in the plane. We have one last pesky detail to figure out here, and it's that this point, the one at the end of the vector from my nose to the screen, this point has to be in this equation. So I'm going to drop those coordinates into this particular thing. So 9 times 2 minus 13 times 3 minus 7 times negative 5 is supposed to be equal to 0. So if I tried that, 9 times 2 is 18, negative 13 times 3 is negative 39, and negative 7 times negative 5 is positive 35. So I end up with 35 and negative 39 is negative 4, and 18 is 14. 14 equals 0. That's troublesome. So the issue is that I used the right normal vector. So I have constructed the Cartesian equation for a plane that is parallel to this one, but it's on my nose. I don't want it on my nose, I want it over here. So the way I'm going to fix that is I'm going to add a little correction factor to my Cartesian equation to make this work out for 0 if I put in these coordinates. So this side ended up 14 too high, so I'm just going to subtract 14 from this. There we go. And so that correction factor, the thing that ended up back here on the end, was the normal vector 9 comma negative 13 comma 7 dotted with the point that was in the line or in the plane. So there's your setup for a Cartesian equation. You take the normal line and you dot it with the generic xyz, and then set it equal to the normal vector dot product with the point that you want to lie in the plane, and then you work it all out into something that looks like that for your Cartesian equation. So I'm going to clean this off, and we're going to try an example, see what we can do. So I'm going to write all three equations, the vector, the parametric, and the Cartesian equation, for a plane that is parallel to this vector, 5, 6, -1, and this vector, 2, 2, 7, but also contains this point, 1, 3, -2. So just reading this in context, because the plane is parallel to this and this, those are going to be my direction vectors. And then this is the point that it must contain. So my vector equation would just be x, y, z equals the place where I start from, 1, 3, -2, plus some number of jumps along this vector, and then some number of jumps along that vector. So that's pretty straightforward. The parametric equations are just isolating the x, y, and z on their own. So x would be 1 plus 2n plus 5p. Y would be 3 plus 2n plus 6p. And z would be -2 plus 7n minus 1p. So there we go. To get the third one, I'm going to have to find a vector that is perpendicular to these two direction vectors, so I'll need to do a cross product. So 2, 2, 7 is my x, y, and z, and 5, 6, -1 as my other direction vector. Copy the x coordinates for convenience. So my normal vector will be 2 times -1 is -2 minus 7 times 6, which is 42. My y coordinates will be 7 times 5, which is 35, minus -2. And my z coordinates will be 12 minus 10. -2 minus 42 is -44. 35 minus -2 is 37, and 12 minus 10 is 2. All right. So I need to double check these to make sure that my normal actually ended up perpendicular. So -44, 37, 2, dotted with 2, 2, 7. Would be -88 plus 74. 2 times 7 is 14. 14, 78, or 88, so that one worked. So that added to 0. Check the next one. 5, 6, -1. Oh dear. 5 times -40 is -200. 5 times 4 is -20. 6 times 30 would be plus 180. 6 times 7 would be plus 42. And 2 times -1 would be -2. So if I look at my negatives, -2, and this would be 40. That's -220. And 180 plus 40 is 220, and that equals 0. So I did it. That's my normal vector. So now that I have my normal vector, to get the Cartesian, I just need to do a dot product with the generic coordinates x, y, z, and the dot product of the normal with the point I'm trying to get to. So just determine that n is -44, 37, 2. So to do my Cartesian equation, I'm going to have to take that normal vector, negative 44, comma 37, comma 2, and dot product it with the generic coordinates and set it equal to the normal vector dotted with the specific coordinates that I'm trying to get to, which is 1, comma 3, comma negative 2. So that would be negative 44x plus 37y plus 2z equals negative 44 times 1, 37 times 3 would be 90 plus 27 is 117. 2 times negative 2 is negative 4. Negative 44x plus 37y plus 2z is 117 minus 4 would be 113. 113 minus 4 would be 109. And 109 minus 440 would be 69. So that is 69. 109, 113, 117. Yep, that worked. And so just to finish it off, I'm going to pull everything over to the left side. So negative 44x plus 37y plus 27, 2z minus 69 equals 0. So I have accomplished what I was asked to do. I wrote the vector equation, that's one of them. I wrote the parametric equations, that's the second. And then I did all this work to get the Cartesian equation, which is my third and final equation for this plane. Now you might be asking yourself, why have I done all this work and have all three equations? So whenever you have different forms, there's always a different application where that form is easiest to use. For example, this one made the most intuitive sense for where you are on the plane. If I give you a set of coordinates, I give you an n and I give you a p, you can locate that place on the plane really easily by just using this form. I can see in this form that I go from my nose to here along this particular vector and then zip around in those two directions. So if that's all you're doing, then no problem. If I was trying to figure out where this plane crossed another one, or where a line intersected this particular plane, I'm going to need my parametric equations. I need to get the x, the y, and the z out of the way so that I can find the coordinates n and p on the plane to find the place where that line crosses. So this format is going to be better for trying to do any sort of intersection. This equation here is really handy if I'm trying to figure out if a point is in the plane. So if I were to ask you, for example, after all of this, is the point let's make up a number 4, that's too big, about 1, comma 2, comma negative 5 in this plane. Well, I have some equations, right? I could put that in. I could put it in this one, 1, 2, negative 5. And then I would be able to solve the coordinates n and p for where that is located. I don't have enough information. Here, I could put 1, 2, and negative 5. I have 3 equations with 2 variables, so I have enough information to try and work it out there. But I'm going to have to do one of those, like, hook 2 together, solve for n, take that n, put it in for p, then check in the z coordinate, the same way that you were checking whether lines were in or whether dots were on lines back in the other section. But this equation down here, if I took 1, 2, and negative 5 and I put them there, there, and there, all I have to do is see if this line equals 0. So that's the handy thing about the Cartesian equation, is it's showing you, like, it's an easy way to check a dot to see if the dots lie in that plane. So let's just do this one quick. Negative 44 times this x value would be negative 44. 37 times this y value would be 74. 2 times negative 5 would be negative 10. Negative 69. Now I can see already negative 10 and negative 69 is negative 79. This is not equal to 0. Therefore, no. That dot is not in this plane. And I checked it using the Cartesian equation.